So Nima is one of the most famous experts in theoretical physics of our time. You can read about his prizes in Wikipedia, and so it was, the information also was sent out. And
thank you. And you know the time. All right. It's really a fantastic pleasure to be here. I'm talking about really a sort of a line of investigation that many friends and I have been pursuing for around 10 years now, centered on an interesting, somewhat surprising connection between some very basic physics associated with the fundamental principles of space-time and quantum mechanics, and some new areas of mathematics that we're sort of loosely referred to as positive geometries, and I'll explain a little bit more what that means. I should say at the outset, one of the funny things in this business for me, so this is the whole sequence of collaborators I had, sort of been the main ones, and they're roughly equally divided between physicists and mathematicians. How does this work?
to the left.
Huh? No, I don't want to. I just want the laser point. Oh, there we go. Oh, wow. That's pretty seriously tiny point. I'll just point. Can I use this? Is this okay? All right, very good. So there's a roughly equal number of physicists and mathematicians on this list. I find myself in the past 5 years, most of my collaborators have been mathematicians. And this is a significant surprise for me. I'm not a mathematical physicist by any stretch of the imagination. I'm a physicist who loves math. That's not the same thing. But what I find interesting about this subject is that there's a centuries-long interaction between physics and mathematics. This is a kind of new kid on the block in this interaction. But what I find interesting about it, and especially in the last 30 or 40 years, there's been incredible interactions, famous incredible interactions between quantum field theory and string theory on one hand, and all kinds of areas in math on the other. But I think it's fair to say that a lot of these interactions involve physical questions that are somewhat esoteric to a red-blooded, experimentalist. So you want to talk about partition function of some fancy theory on some fancy manifold, or you want to talk about, and these are deep and very important things. They probe the structure of quantum field theory, they're profound, all that, wonderful. But they're a little not obviously connected to the sort of everyday concerns of what you might call a normal, non-mathematical physicist, what I thought of myself as for example. And the startling thing here is an interaction between new areas of math and bread and butter basic physics. So, the star of what we're going to be talking about here are simple experiments that our experimental friends do all the time. The mathematical structures I'm going to tell you about describe the actual real world in some leading order of approximation. Okay? They're not exactly the real world, but in some leading order of approximation, high enough energies where you do the leading approximation to various processes, we're going to see some connections between that physics that's happening in Geneva every day of the week, is happening when cosmic rays hit the top of the atmosphere at high enough energies, millions of times a second, and what kind of structures in mathematics, and that's a surprise. There are structures that involve ideas in combinatorics, positive geometry. They're attached in interesting ways to number theory and other things that are at least ahead of time, not remotely obvious that these things should have anything whatsoever to do with each other. And so that's what I'm going to try to convey in this talk, is A, what the physical questions are that are involved and why they touch so immediately and directly on these foundational principles of space-time and quantum mechanics. Why it is that we have many circumstantial pieces of evidence that we should learn to think about space-time and quantum mechanics in a different way. And B, the kind of mathematical ideas. And, I can't in an hour, if you're lucky, I can't give you a really detailed overview of everything, but I'll try to give you enough concrete examples so that you have some idea of what it is that we're actually doing. Okay. In any case, that's how I got dragged into the subject as a non-mathematical physicist by the physics, by following this surprising physics where it was taking my friends and I. All right, so just a few quick reminders of where we are in fundamental physics today. The 20th century started with these two giant revolutions, quantum mechanics and Einstein's picture of space-time. And much of the second half of the 20th century, starting in the 1930s, but going to the second half of the 20th century, maybe to the 1970s or so, but continuing to this day in many ways, has been about learning how to describe universes that are compatible with both of these principles simultaneously. Okay, so, and it's non-trivial to come up with, it's non-trivial to have the world compatible, laws compatible with both quantum mechanics and space-time. Let me just give you a 30-second reason why, if you don't know this. Einstein's picture of space-time, mixed space-time, space and time are not as different as they were before. You could mix space into time by Lorentz transformation. So time and space are not so different. Okay, quantum mechanics changed everything, right? Much bigger revolution. Changed the grammar of physics, what physics is supposed to be about. We can only predict probabilities, evolve wave functions, et cetera, But the one thing that didn't change was the primacy of the notion of time. You give me the state at one time, you evolve to another time, and time. Okay, so time is important in the standard quantum paradigm. Time gets mixed into space in the relativistic paradigm. So if you were to hand a mediocre theoretical physicist, if you were to hand to me in 1935 on that scale, the laws of relativity and quantum mechanics say, go, make universes that are compatible with both of them. I would look at one, I'd look at the other, I'd say it can't be done. Okay? But it turns out that it is possible. You have to choose very special kinds of quantum mechanical systems that, despite picking a time and making it special to evolve, nonetheless give you answers that are symmetrical between space and time in a way dictated by relativity. And that synthesis is what's called quantum field theory. Okay? And quantum field theory is the space of all possible laws of physics that are compatible with these principles of relativity and quantum mechanics. Now, a very particular quantum field theory describes the elementary particles and interactions of the real world. That's a standard model of particle physics. And so you could study that quantum field theory. It has, it turns out, lucky for us, nature has provided a quantum field theory that has lots of richness in it, so a lot of the dynamics and non-triviality of quantum field theory we can even see in the real world around us. But a lot of the activity in theoretical physics for the past 30 or 40 years has been exploring the theoretical structure of quantum field theory and trying to understand it better. And of course, that's been one of the great sources, as I mentioned, of this amazing revival of interactions between mathematics and physics. Okay, but what are the storm clouds of this picture? So on the one hand, we have this quantum field theory. The structure is very rigid. A particular one describes nature. We don't have any evidence even that that particular one is even modified or extended in any way, to the great chagrin of all sorts of people who are waiting for it to at least break or be extended a little bit. Still, there's no evidence that there's even the slightest thing wrong with it at the energy scales that we're probing as accelerators today. But there are definitely theoretical reasons. There are big storm clouds, and the storm clouds aren't in random places. They're about exactly the foundational principles that go into this spectacularly successful framework to begin with. Because of gravity, we have very good reasons to suspect that the notion of space-time itself is approximate. So that was one of the pillars, but because of gravity and quantum mechanics, space-time is likely doomed. And it's even possible that there are limitations of quantum mechanics when we ask, I'm not saying quantum mechanics is wrong or modified or anything stupid like that, but I'm saying that there are questions that involve applying quantum mechanics to the entire universe where the usual rules for thinking about what quantum mechanics lets you talk about fail. And quantum mechanics cries uncle, and we don't know what we're supposed to do. So there's at least an indication that we have to extend quantum mechanics in some way. Not that it's wrong, but it has to be extended. All right, so here are some of the simple thought experiments that tell you that are associated with these big conceptual paradoxes. For instance, This is why space-time is doomed. One of the zillions of reasons why it's doomed. We'll talk about a deeper one in a second. But if you use my crappily drawn magnifying glass to try to look at some region of space and time to see what's going on in there, take a microscope and look at the vacuum, by the uncertainty principle, you know you have to put more and more energy into the smaller and smaller region of space. That's why we build gigantic particle accelerators and smash particles into each other at very high energy. The irony that the largest machines that we've ever built are probing the tiniest distances we've ever probed is a direct reflection of this basic fact of the uncertainty principle. Okay? And in a world without gravity, you just beg for more and more money from bigger and bigger multinational governments, and off you go. Okay? But in a world with gravity, you have a fundamental problem that eventually you pour so much energy into such a tiny region of space, E equals mc squared, there's a huge amount of mass in that region, and so what happens when you put enough energy into a tiny region of space? It collapses into a black hole. So your attempt to see what's going on inside is stymied by the act itself. You produce a black hole that makes it impossible for you to see what happens. And if you get frustrated by that and say, shoot, I'm going to build an even more powerful accelerator, more powerful microscope, what happens? You make an even bigger black hole. Okay? So this means it's a very basic thing. This whole reductionist paradigm, the whole thing, we go to the very shortest distances, everything is fundamentally defined now, is wrong. We know it's wrong. Today we know it's wrong. We don't know what replaces it. But the idea that everything is fundamentally given at the shortest distances is false. And somehow very, very high energies turns into very, very long distances again. And there's no operational way of talking about space and time separations that are small enough. When does this happen? When we get to the famous Planck length. And when you put so much energy into such a tiny region of space, around 10 to the minus 33 centimeters, 10 to the minus 43 seconds. By contrast, the distances we probe with the Large Hadron Collider today are around 1,000 times smaller than the nucleus of the atom, around 10 to the minus 17 centimeters. And so this is 16 orders of magnitude removed from that. The tininess of these distances is a reflection of the incredible weakness of gravity. Okay? But nonetheless, it's true, we can do this thought experiment. So we learn gravity and quantum mechanics means that space-time is doomed. There's actually a deeper aspect to this problem. That might make you think that the difficulty is somehow restricted to very tiny distances. It might even make you think some dumb ideas, like maybe if you go to really short distances, you'll see that space-time is a lattice or something. Or there are atoms of space-time. Some, like the table looks smooth, but at very tiny distances we see that it has some discrete structure. That idea cannot be right. It cannot be right for many reasons. Part of it is the reason why the table can have structure is that there's a thing there. There's a material thing there. It chooses a frame of reference. And we can measure whether we're moving relative to the table, to the frame where the table's at rest or not. Another way of saying it is if there are atoms of space-time, they have to be small. But who sees them as small? Special relativity tells you that lengths can change depending on the relative velocities that you're given. So any of these discrete ideas, these naive discrete ideas, are doomed to be in violent disagreement with even the success of special relativity. So it's not something silly like that. It's not just some way of modifying things at tiny distances. You can't just do something dumb like that. But in fact, it's even deeper than that. It's not just that the notion of space-time has got to be modified in some way, like the notion of surface of table has got to be modified in some way. But in a deeper sense, the notion of the inside of a space-time is simply false. It doesn't exist, really. It can't be given any operational meaning.
But isn't the Planck length the smallest distance they can ever exist? So the discrete does make sense.
Well, so this is the challenge. That is a fact, but that fact cannot be is not effectively modeled by theory that says, oh, there's just some little discrete chunk sitting there. Because if you have that, you're dead. If you have that, then
maybe there's something else.
Then there's something else, and that's the something else is the sort of thing that's the big question. Now I'm telling you another conceptual fact, and I'm going to say just another 5 minutes of general facts like this, and then we'll get to more beefy things. So another fact about quantum mechanics is that in order to talk about anything precisely, any observation precisely, quantum mechanics needs two infinities. You have to invoke two infinities. First of all, it's a probabilistic theory. So I can't predict what happens in the future exactly. I can only predict probabilities. To make a probability sharp, I have to do an experiment infinitely often. Okay? Secondly, something we talk about less, this one we emphasize when we teach quantum mechanics, and it's even important. You guys are mostly mathematicians, but if you're an experimentalist, this thing that you have to do the experiment over and over again, since you can't do it infinitely many times, if you do it n times, you're forced to say in your talk, there's an error of order 1 over square root of n. It's called statistical error. And ultimately, that's quantum mechanics. Okay? That's this trials factor. Okay? There's another one, which is also important. It's practically much less important, but it's conceptually important. You have to do the experiment with an infinitely large measuring apparatus. And that's because the apparatus itself is quantum mechanical. If it's going to register some actual answer, then it can't, if it's made out of a finite number of parts, then it's also quantum mechanically fluctuating. Just to give you a concrete example, let's say I want to measure any physical quantity of any sort. Doesn't matter what. Pick your favorite one. But I want to measure it to the accuracy 10 to the power of, this is very ridiculous, but 10 to the power of 10 to the 40 decimal places. Okay? Now, I can't do it because I'm made of around 10 to the 30 things. And by the time I get to around the 10 to the 10 to the 30th decimal place, all kinds of terrible things can happen. I could fluctuate into a cloud of dust. Okay, that will obstruct me from writing down the answer. One of the more mild things that can happen, my brain could have a quantum mechanical fluctuation. Even though I should have written down 7 to the 10 to the 10 to the 30th decimal place, I write down 2 instead. Okay? So any finite system has an irreducible amount of systematic error associated with anything you can talk about of order e to the minus n, where n is the number of things it's made of. All right? So, now that's why we don't talk about it practically. Nobody cares about that one practically. We care about the 1 over root n practically. But both of these infinities are needed. And once again, in a world without gravity, there's no problem in principle of achieving both infinities. And that's what quantum mechanics asks you to do. You know, that's the Bohr and Heisenberg and all these people understood it. And some of this was revived in the 70s and 80s under the name of decoherence theory and stuff like that. I think they added maybe 0.5% to the story that was 99.5% understood by the founders of quantum mechanics already. It's a very profound and important point. You have to drag these infinitely big apparatuses around with you everywhere you go. And you see, without gravity, that's fine, but gravity doesn't like that. Gravity doesn't like to divide the world into 2 pieces, an infinite part and a finite part that's doing the looking. And so there's an obstruction. If I try to do an experiment in a fixed size room, if I try to make the apparatus bigger and bigger, what happens? It gets heavier and heavier. And if I'm doing it in a fixed size room, it will become so heavy that it collapses the whole room into a black hole. And then I can't do the experiment over and over again because I get sucked into the singularity and then killed. So that means that there is no operational way to talk about any observation in some interior region of space and time. This is a really remarkable fact that has to do with this basic, the basic existence of both quantum mechanics and gravity. Something that was well appreciated by a variety of people in the 1960s already. So what kind of things can we talk about? By the way, why do we care about this? We care about this because we're used to talking about precise mathematical theories in physics. Okay? So also when you go from classical to quantum, you could say, who cares about the uncertainty principle? Practically speaking, I do know the position and velocity of a baseball at the same time. Okay? But it's really important, even though it's practically irrelevant, to know conceptually that the word position and velocity is replaced by position or velocity. It's the most profound shift that you can imagine. Okay? So similarly here, we focus on questions that could have precise answers, because that's what a precise mathematical theory should be about. It should give us, there's a formula in some theory we're looking at. What is it computing? It can't be some fuzzy thing. It has to have something that has meaning, real precise meaning. And so that's a trajectory we've been on for over 100 years, to take this attitude seriously and to ask questions that have precise answers, even in principle precise answers. Now, gravity and quantum mechanics tell us that the only questions of that sort that we can ask are ones where we take those apparatuses and we move them to infinity, where they can get larger and larger and farther apart from each other, and they fire particles into the interior of the space-time. They can bang into each other and do their thing and come back out where they're measured, again, by these infinitely large apparatuses in the future. Okay? Those kind of experiments are scattering experiments. And because the world is quantum mechanical, we can't predict precisely what happens, but we can talk about the scattering amplitude, whose mod squared gives us the probability for the scattering process. Okay? So those are the observables that we should talk about. Now this was very highfalutin, very sort of almost philosophical stuff. Fortunately for us, these observables that are the ones that are precisely defined when you have quantum mechanics and gravity are also the ones that are the bread and butter of research in fundamental physics. Okay? Because that's what our experimental friends do at the Large Hadron Collider. They scatter protons, this ring that goes 27 kilometers around, they scatter protons at 0.9999999 times the speed of light. Of course, they're not coming in literally from infinity and going out to literally infinity, but the proton is 10 to the minus 14 centimeters big. The ring is 27 kilometers around. 27 kilometers is more or less infinity compared to 10 to the minus 14 centimeters. And so these experiments are very close to the ones which are the conceptually clean ones that we're allowed to even talk about when we have quantum mechanics and gravity. So this is an interesting connection that on the one hand, for these deep reasons, we're supposed to say that these are the observables we talk about. On the other hand, those are the good ones too. They're the ones that we actually care about and have been using to unearth the mysteries of the interactions of elementary particles for almost 100 years. Okay, now, this basic ideology that when you have quantum mechanics and gravity, you need to go to the boundary in order to talk about observables, as I alluded to already, was appreciated well by people like Bryce DeWitt and Roger Penrose in the 1960s already. And it sounds a lot like what many of you may have heard of as the holographic principle, the idea that somehow, again, there's a theory that lives on the walls somewhere that's supposed to describe, like a hologram, what happens in the interior. And the last 20 years, and continuing for very good reasons, of research in this part of physics, especially by string theorists, has been dominated by an amazing concrete example of this ideology in action. That's this famous correspondence between theories of quantum gravity in a d plus 1 dimensional anti-de Sitter space and a quantum field theory that lives on the boundary of that anti-de Sitter space. And this is, I think you can think of this as a gateway drug into the idea of emergent space-time. And it's a gateway drug because it doesn't force you to go all the way. You, in particular, don't have to talk about emergent time. Time is left alone. It's really emergent space and gravity and strings and all the rest of it. But you're still talking about ordinary physical systems in an ordinary and familiar language. So what's the picture? Physicists love to put things in boxes, and so anti-de Sitter space is a perfect box. This is one way of drawing the geometry is like the inside of the cylinder. There's a warped metric inside, which means that the distance from any point on the inside to the boundary is infinite. That's good, so we have all this room to move the apparatuses out and talk about these precise observables. On the other hand, the time it takes for a light to go from the middle to bounce on the inside and come back in, it's finite. Okay? So in many ways, it's like putting the system in a box. And now you can ask, what are the observables you're allowed to talk about? If you ping things on the boundary of the box, one way of thinking about things is waves go in, they bang into each other, waves go out. But from this ideology, once you know that those are the observables, you might wonder, is there a way of computing them some other way where you never talk about the inside? You're not there on the inside. All you get to do is ping things on the walls. And the amazing thing is that there is. That a good old-fashioned theory of ordinary particles, very close cousins of the theory of the strong interactions of quarks and gluons that we'll be talking about more. When the interactions between the particles become so strong that the particles and antiparticles are produced all the time, and you can't keep track of the individual properties of each one of the particles that's being produced, and it's useful to use a kind of it's useful to talk about them more collectively. The more collective description of this very strongly interacting theory of good old-fashioned particles turns out to be equivalent to having, in this holographic way, an extra dimension of space, many extra dimensions of space, strings, gravity, and all the rest of it. So this is the subject of many colloquia. You've probably heard many colloquia about it. I won't be talking about it more, but this is the first working example. I'm really working in now understood in great detail and also continuing to be explored from many points of view. However, this is not the real world, and it's not close to the real world. These questions, we're not these observers. First, we don't live in anti-de Sitter space. That's a kind of maybe a minor detail from some point of view, because maybe if we didn't do detailed cosmological experiments, you could say maybe we live in a negatively curved universe whose curvature is 10 billion light years. Okay, maybe. But secondly, we don't ask these questions. Okay? We're not living out of the walls of the box. We don't ask these questions. We're doing our thing on the inside here, right? So this is pretty far from telling us something about the real world, despite being conceptually extremely important. If I jump in the opposite direction, let me tell you what the hardest problem is that we have to deal with. Let's talk of the actual real world. The geometry of the actual real world is cosmological. Okay? Time is not, it's not some static thing. The previous picture is like a static tin can that lives forever from the infinite past to the infinite future. Here we have some kind of birth at the Big Bang that we don't understand. The whole notion of time begins at some point. And then even more disturbingly, late in the universe, we learned in the late 1990s that the universe is accelerating. And that imposes a fundamental finiteness on our understanding of the world. Because what we see now in the universe is what we're ever going to see. Things that are far enough away, the accelerated expansion means that light from them can never make it to us. So in a really fundamental sense, we have access to a finite amount of stuff. And it's a huge amount of stuff, but it's finite. And that finiteness should raise your alarm bells when it comes to a quantum mechanics, right? Because quantum mechanics needs these infinities. Quantum mechanics needs you to divide the world into an infinite piece that's doing the looking and the finite pieces that look at. And that we can't do that.
But quantum mechanics may not be complete.
Well, so that's what I'm saying. So there are two differences here between the actual real world and the world in a box that we talked about. First, time is a big deal. And secondly, maybe we need some extension of particles. So I was jumping from something very actively studied, not understood, but a huge amount of non-trivial evidence that we know what's going on, to this is the hardest thing where we have no idea what to say. And now I'm going to come back to an intermediate step, to an intermediate place where we can try to explore some of these questions and make some progress. What I want to stress, though, is that the central mystery in this whole subject is time. And this was a question that actually bothered people going all the way back to the 1960s when they were just asking it in the context of particle scattering experiments. And that was the question they asked. We scatter particles. We're not inside the protons when we scatter particles. How the heck do we know what happened? That they hit each other and some particles inside hit each other, then this happened, then that happened. All those words, which it sort of invokes some kind of local picture of processes happening at tiny scales. We're not there. How do we know that's happening? All we have is this information from all the plots that we make. The particles go in, the particles go out. So what feature of those answers have a thumbprint on them of coming from causal time evolution? Causal and unitary quantum mechanical time evolution. And we have similar questions that we can ask about cosmology as well. And this is not a technicality, but we don't know the answer to this question. If I hand you a bunch of putative scattering amplitudes and say, can you check whether this came from causal unitary evolution? We don't know how to do that. To this day, we don't know how to do that. Okay? It's not a technicality. It's a question about time and dynamics. So why do we think we can do better? People already asked this question in the 60s, and they famously got essentially nowhere with it. Okay? There was something called the S-matrix program in the 60s, and they thought that all they had to do was impose the conditions of causality and Lorentz invariant and unitarity are easy to check, and causality, and that would sort of uniquely fix the answer. And their problem was that it was based on a fundamental lie that they knew, of course, that we knew ahead of time what that imprint of causality is, and we don't. So that's why if you had the misfortune, if any of the physicists here have had the misfortune to read any of these old books, they're constantly cheating. They don't know what these rules are. It's somehow related to the analytic properties of the functions associated with the scattering amplitudes, but they keep staring at Feynman's diagrams to get a guess for what it looks like and coming back and pretending that they didn't look and seeing if that was enough and going back and forth, and they didn't get anywhere. So what can we do better now? What do we have going for us now that they didn't have back then? There's lots of technical things, but there's a more important strategic thing, that there's a fundamentally new strategy that many of us are pursuing. You see, back then, people thought that they could sort of responsibly derive somehow from the bottom up what the rules of causality, how the rules of causality should be imprinted on the scattering amplitudes. And now we have an opposite attitude. We don't want to derive it from anything. We're much more irresponsible. Okay? What we want to do is look for some new principles, laws, structures that determine some answer, and then see how causality and unitarity come out